Hello friends, welcome to episode 8 of Kermit GNC. Let's build together. Today we will build the equilibrium of our system. For all of you controls engineers out there or flight simulation engineers, GNC engineers, you know what I mean when I say equilibrium. In order to design any kind of control around a system, you want to make sure that your system is operating at an equilibrium. A system usually it can have one equilibrium or more than one equilibrium, but you want to be at one of the available equilibrium in order to design any controls off of it. So that's what we are going to build, and engineers usually call it trimming the aircraft. And when they say trimming the aircraft, you know they are talking about getting the equilibrium. That is different from when pilots say trimming the aircraft. For them, it is the trim wheel present inside the cockpit. But today, we are going to work as an engineer to get our trim equilibrium figured out. So this will be a 2-episode long concept. So today we will do the longitudinal equilibrium part of it. For the longitudinal equilibrium, you want to basically get your fx, that is the trim version of fx, to be 0, fz to be 0, and all the moment to be 0. So that means think of straight and level flight, right? On a straight and level flight, your lift is equal to weight, thrust is equal to drag, and there is no net moment, so there is no pitch, roll, or yaw. That is one of the equilibrium cases. So therefore, the f of x, f of z, and m being equal to 0, it's the universal way of approaching equilibrium concept. But if you do small angle approximations, then you can get the set at the bottom. We will do the first one. So in the end, I will do some analysis to show you that we are getting f of x and f of z and m to be 0. The other version of that is our 6 degrees of freedom 6-stuff block from the Simulink that uses integration inside, which means in the end, we also want to check that our p, q, and r is pretty close to 0 or equal to 0. And I will show you how we can improve our pilot controls or pilot commands subsystem. We will design a subsystem around it. I will show you how you can use manual switch. We will talk about trim algorithms that are out there. And to begin with all of that, let's discuss flight path angle. Flight path angle is basically the angle between the horizon and the flight path vector. A flight path vector is where the flight is going, not where the nose is pointed, where the flight is going and traversing the path. So that is usually denoted with gamma, and gamma is equal to theta minus alpha. For a trimmed airplane at equilibrium, you want your flight path angle to be 0, which means your theta will be equal to alpha. Hold on to that idea because that would be the key idea we will build off of. Let's go to our model. So we stopped with this version of our model, if you remember. Now, if you are new to this, I highly, highly, highly recommend you check out all the episodes in the series up until now in order to make any sense out of this. And the description is below. So let's start by making this simpler. So the pilot command here, I will create a subsystem off of that. And this will be my pilot command or pilot controls, whatever you want to call it, pilot command. Okay, let's click on these 1, 2, 3 outputs. We don't want any output off of this system for now. So there goes that. Now, next thing is I want to go inside the pilot command. And if you recall, earlier we were doing analysis where we had to comment out a couple of the blocks, but I am going to change that. So instead of having to comment out, I will do a manual switch where we can make both of the types of input available for our advantage. Before that, okay, so what I will do is I am going to remove this and double click, get manual switch. Okay, let's get 3 switches for each of the aileron deflection, rudder deflection, and elevator deflection. There goes that. And then I will connect the slider to one and signal editor to the other one. Similarly for the rest of these. what that will do is I won't have to comment out these features every time I need to use them. So if you double click on the manual switch block, you can toggle the switch. I will toggle the switch downwards because for today's analysis, I will use the slider. So signal editor can stay. It need not get commented out. And the ones that were already commented out, if you click on them and hover around the three dots, you will get a chance to uncomment those. So we are going to uncomment all of these. Hopefully this will reduce the hassle of going back and forth between signal editor or manual pilot command or manual slider, So there is that all got taken care of. The other thing is over here for the throttle Tmax, what I will do, I'm going to remove this gain. And instead, I will use a constant. This is a workaround I am doing in order to capture the maximum throttle available to me as through a go-to block, because we will need that in our trim or equilibrium algorithm. So I will double click, make the go-to block visibility global, and let's call that Tmax. And for here, I will use a product and connect the product block to the rest of it. This workaround we will end up doing at some other places as well, so stay tuned. Okay, there is that, and Tmax double click, let's make it 2500, which it was in the beginning. Let's connect that properly. There we go. Okay, another thing we need to do is, let me push this up. The slider can stay inside. Okay, now I'll make that tad bit longer. Okay, here I will use a from block because I want to use my throttle trim offset to add up to the rest of it. Now we have done another episode on the elevator trim, if you remember, and that was episode 5, I believe, that we designed. It was the trim wheel design kind of concept. So what is available in the cockpit, that had to do nothing with this equilibrium solver design. So it may look similar to that, is what I'm trying to say. So this del E trim offset, if you remember, this offset comes from that other elevator trim wheel algorithm. We will change that to the equilibrium trim as well for now. And later we will develop the autopilot system a little bit later. Okay, let's get on the trim algorithm. So I'm going to use a constant because this constant is going to be my desired velocity command, where I can put a desired velocity I want the equilibrium to work around. So let's call that 50 meters per second, since all of our units are in meters or in standard units for now. So let's start the the equilibrium solver algorithm. I will call equilibrium for the rest of it, but it's trim equilibrium used interchangeably. What I will do is I need to get integrator blocks. These blocks are pretty good at capturing error for a long time and then canceling those error. That's what basically these integrator blocks are used for. Well, one of the applications, right? Let's make a subsystem off of that, and let's get rid of these inputs and outputs because these are not our desired inputs and outputs, right? So okay, now this V desired can go in. Let's double click in the subsystem. Here is our V desired. And then let's make another subsystem over here. The reason I'm making subsystem inside of a subsystem is because I want to call this longitudinal. And later we will work on making lateral subsystem over here, right? So let's get rid of all of these inputs again and outputs again, and connect the V desired in here, double click. Now we will start our work. I am going to label this as V desired so we know. Okay, now going into the trim equilibrium subsystem, we will arrange these ones properly. So the first integrator, that is going to be my alpha trim. So alpha trim. The second one will be elevator deflection trim, elevator trim, and last one would be throttle trim. These are the offset numbers that will feed into the main input command, right? So for each of these, for alpha trim, we will give that initial condition. Let's call that a little 3 degrees of initial condition, which in radians it is 0.5236. So that is like 3 degrees. I can use this annotation feature on the left here and just use that to give annotations, which will help me to keep things straight like that. Elevator trim can stay 0. Throttle trim, double click. Let's make that 0.5 for now. Okay, now we want to do saturation because these are important parameters. We don't want the airplane to go beyond a limit. So this is saturation. We will make this alpha trim saturation to be -10, +15 in degrees, which will be these values in radians. Okay, now for the elevator trim, we will make that positive -25 degrees, which will be that in radians, because we have to put all of these in radians. And then the last one for the throttle, we will keep it fractional. So 1 for the upper limit, 0 for the lower limit, as simple as that. Okay, with that, let's capture these. So I will use some go-to blocks. Let's call this one. Once I get the signal out. Okay, there goes that. And this one can be alpha trim. Let's make that visibility global so we can use it elsewhere. You can make that longer to see the name. This will be del E trim, visibility global again, and this will be throttle trim, visibility global. Okay, and now we will use a gain for each of these because we want to have a gain value so we are able to tune it properly. So there goes 1, 2, 3. Okay, I will use this area feature for annotation purposes. So I'm going to use some annotation to make it cleaner, just like that. And that piece is solved. Next, we need to find fx, fz, and m, which I showed you in the beginning, right? Because that is the end goal. We want to get fx, fz, and m to be equal to 0. You may ask, why not fy? The reason is, and also you may ask, why not the other components, which is L and N of the moment? Again, you may have guessed it. Reason is all of those are tied up with the lateral directional equilibrium idea. So we will play with them next time. For now, we are focusing on these only. So you can see V desired can be used here. V desired is our command velocity. And then let's get a cosine. We need a sine. And if you notice, it's all getting multiplied. So we need a product. I'll make 3 or 2 copies of them, and this will be cosine of alpha trim. So alpha trim is already available right there. I can use the same signal, and then this will be velocity desired, like that. Okay, that takes care of both of those. And then theta trim is nothing but alpha trim, so I'll just use a go-to block to capture that. We will probably need it. We will see. There is global let's keep that local for now. This can stay local visibility because I won't be needing it elsewhere, but I will keep that in mind. And that will also connect to alpha trim. With that being said, let's put an area for all of these, since we are pretty much done with this piece now. Using this area annotation comes in handy because that way you can use the box to move around things, but also you can keep things as clear to understand as possible. Now, if you recall, the next item here is after you get your components of velocity, you want to calculate the magnitude of the velocity, right? So this time this will be v trim, and that is nothing but a square block, and so we get 1, 2, sum, okay, and square root, and that gives us our v trim. So this will look familiar. We have done the same thing when we were playing around with our aerodynamic block set, and this is the same idea because you can see we are finding force and moment, which we all have done it before one time, and so it's literally the same thing. The only difference is this time we are using the trim components, not the regular ones. So now we will find our dynamic pressure, trimmed dynamic pressure, right? So we need a constant block. Another idea is you don't want to redefine variables that have already been defined elsewhere. Hence, you use go to and from blocks because, of course, you can guess if you define the same variables at multiple places. Later, if you have to change them, you may have to change them at all different other locations, which would not be a good idea. If you really want to automate your system, the best way you do is, if you have defined it elsewhere, use go to and from block to capture it. So rho is already defined in our aerodynamic block set. I can go grab that and use that from there. So here is v getting squared again, and I will use that as one of it. Rho will connect there, and 0.5 factor will go there. Let's go to the top level. Aerodynamic block set. Q bar is here and rho is right there. Let's use a go to capture the rho. We will have to do back and forth a little bit to capture a couple of the items, but I will point it out. You will be able to see how we do it. Okay, so back to the equilibrium, and then now I can select rho from my list, which is right there. So that will give me my Q trim. Now that can be put into another area. Okay, I will show you a couple of other items that can be done now, which go in parallel. So I will leave them right beneath this set of 4 blocks, and then we will proceed across. So CL trim version and then CD trim version is what we need next. CL is your lift coefficient, CD drag coefficient. Formulas are same formulas we have used before. And so over here, if you notice, I am going to use a couple of from blocks because some of these items are already defined in the aerodynamic block set. We can go fetch from that. So CLO, CL alpha, CDO, and K are already defined. So let's go to the top level aerodynamic block set. And over here we have CLO. So let's use a go to block to capture CLO. There goes that. Double click. Let's call it CLO and tag visibility global. Okay. Now CL alpha is again a gain. So a workaround with that is cancel that. Use a constant. It was 5.5 before I forget. And then this is CL alpha, right? So I write that down, CL alpha, and then I can use a product. Exactly what we did with the throttle system earlier I showed you. Okay, and then CL alpha goes there, and now I can use another go to block to capture my CL alpha from that signal. Okay, let's call that CL alpha tag visibility global. Make sure to always make your tag visibility global for these transferable parameters. If not, then you will see error messages. It will not migrate from one subsystem to another subsystem. Okay, let's get our CD. You can use Control plus R to rotate CD. Okay, and now go to block here will get us CD. If I can connect it properly, there you go. Okay, and then CDO tag visibility global. Perfect. And then this K, same workaround. So let's get rid of the gain block. Okay, 0.04. And this is my K, so I will get the label back up, and then product. Let's connect that. Okay, there goes one, there goes two, and then another go to block will get me my K from here. And double click, K, tag visibility global. All right, all of that is set. Let's go back up to the equilibrium. I will label this as we are here. Equilibrium solver. How about that? I will call it trim/equilibrium solver because I want to point out the fact that this is also called a trimming the airplane, which is different from when a pilot says trimming the airplane. So I want to emphasize on that several times. Okay, now let's get our CL alpha here. There is that, and don't hesitate to make these blocks bigger so you can see their names. And then that can be CLO, and this will be our K. Okay, and then this one is CDO. Perfect. Now CL alpha times alpha. So let's get a product. And I will make a copy of that since we need that here as well. Okay, K can go there. And then CL alpha times alpha trim. And alpha trim is already available to us over here on the top. So there is that. Easy. Okay, now we need a summer. So here is a sum block. And 1, 2. And if you notice, the same thing feeds into it. So I can use a square block and then feed this to my CD area. And let's see, we need a summer for that. So let's use another sum. Okay, there is one and there is the other one. All right, with all of that sorted out, let's put some areas around them. This is CL. I want to keep this intact like that. Okay, and then let's put another area around CD. Perfect. Okay, now another thing which we can get in parallel to all these guys is our CM trim term. If you remember, this is going to help us to get our pitch moment M. This is pitch moment coefficient. Now here CM alpha and CM del E are some of the things we can capture using from block because those are already defined, right? So we will go into our moment subsystem to get them in a second. Let's do a product because both of those will be products of each other. 1, 2, and then we need a sum to add them all. 1 and 2. Okay, CM alpha and CM del E. All right, let's go to the top level, moment, and CM alpha is right there and CM del E is here. This is the easy one, so let's grab this first. Here is go to block to capture it and double click CM del E and tag visibility global. Okay, and now we need CM alpha, but here is another gain thing. So let's get rid of the gain, use a constant, and this can be negative. Let's call it 0.5. And CM alpha, this was CM alpha. Okay, and with that, I need a product. Now, if you don't know what each of these variables are, like what is CM alpha and things like that, if you remember, I have given you a cheat sheet last time. You can make use of that. If you don't know, do check out the previous episode to grab that cheat sheet and use that wherever you like. All right, CM alpha is here now. So let's actually use a go to block and capture that. So I will call that CM underscore alpha, tag visibility global. Since we are here, I will also capture little c, which is already present here. That is our mean aerodynamic chord, MAC. We are going to need that in just a little bit, so why not just capture it as we are here. Okay, I think that's all. Let's go back to our equilibrium trim solver. All right, let's put CM alpha right there. and I will put CM del E there. Okay, let's zoom into it and make them bigger so we see the names. Perfect. Okay, with that, the only other thing we need is CM alpha times alpha trim. So CM alpha times alpha trim, that's that. Okay, that looks better. And then CM del E times del E trim, and we have that. We have del E trim, if you remember, right there. Okay, and then let's make these wires slightly better. Perfect. Okay, that takes care of our CM trim. All right, all of these can be called as one primary level, if you want to call it. So what I will do is I will make a box around them entirely, and let's actually just color that box right like that. Okay, that takes care of the primary level. Now let's do the secondary level, which will use the input from the primary level. So for the secondary level, we will do, let's see. So from the secondary level, I am going to calculate my force parameters. So I will get my moment. Let me put the formula so you know what I am getting next. So I will get my moment, pitch moment specifically, and I will get my lift force and drag force. So let's get those three first. Well, how about I just put all of them? Maybe that will be better. So then I need my gravity terms, especially the x component and z component of gravity. And I will need my throttle configuration for the trim throttle input, like that. So these are the 6 things we are going to get here, and that would be our next level. So let's dig into it. Okay, I need a product. Let's make that double click, make that 4 channels product, and then I can make 2 more copies of that because I can use them for my drag calculation and lift calculation. And so for drag and lift, 3 channels will be sufficient. And if you notice, each of them is using Q trim. So I can put Q trim like that for all of them. Okay, and then I need a from block. Well, actually 2 of those to get my C, the little c, and S. So little c will be right there and S will be right there. Okay, so S can go to all 3 of them because all 3 of them need S, and little c can connect there like that. Let's see if we can make that a tad bit better. Okay, nice. And then we need CM trim. CM trim, if you remember, comes from this one. And for this, I need CL trim. CL trim is right there in the middle. So there goes that. And then for this one, I need CD trim. So those are all done. Let me put areas around them since I want to keep them separated out. It is so easy for the eyes to even fathom where is what concept being operated on when you have these things with the area annotation like that. Okay, and I need, all right, almost there. All right, so those are those. Let's go down. We want to do these 3 guys now. So we need FG, FGX, FGZ, and throttle trim. So all 3 need product. So there goes that. 2 more copies. 1, 2. Okay. Now I need a sine and I need a cosine. And I need a from block to capture my weight from outside, and we will use that weight. So I'm going to leave it here for a second. I think I will leave it right there. All right. This is sine of theta trim, which is also alpha trim. If you remember, theta and alpha were same things. So you can get it from wherever. I will connect it there. And then same cosine can go there. Okay. And then for the throttle, we need Tmax. So a from block will get us Tmax, and let's get Tmax there. And then you can get the throttle trim. You can use the from block to capture throttle trim, or you can just hook up a wire like that, whatever is convenient for you. Okay, so throttle trim is already sorted. Let's put an area around that. And now let's go fetch weight. So it's in the aerodynamic block set up top here. FG subsystem has the weight over here. So we'll do a go to block and we will capture the weight. Double click, call it W, tag visibility global. There goes that. Let's backtrack to the equilibrium solver, and there is weight, sine of trim, weight, cosine, like that. I could have done that better. Let's see. Just like that, yeah. And then this one needs a gain of -1, as the formula has it. There is that. Perfect. Okay, let's put 2 more areas around them. And with all of that, this entire system is built up. Now we are pretty close to getting our final force and moment, which will feed back into the integration loop. We will get there. We are building it up. Okay, I will zoom out a little and make sure I have fixed all the sizes. So it's gonna be able to fit inside the bigger area I will put around all of them, since this is level 2, like that. May have to zoom in to capture. Okay. And there goes that. All right, let's do that yellow color. Perfect. So that takes care of all of that. The next level is I will be building my forces. So one is my FZ force and the other one is my FX force. So I will use a sum block for this, double click. This one is gonna be negative, negative, positive, and I can actually zoom in, make this a bigger one so it's visible clearly. Let's get another one of those, and this will be negative, positive, positive, just like the signs are in this formula. Okay, with that, we need the middle term is a product. So let's get a product. Okay, and then that one is actually multiplying sine and cosine. Okay, we have it. Let's do that. So D trim is right there. And this is also taking D trim. And then this one is sine of alpha trim. If you remember, sine of alpha trim is here. Alpha trim, theta trim, both are same things. And this is cosine of alpha trim is right there. The next thing is this entire piece is a negative. There is that. Okay, and this entire piece is a negative. So there goes that. Another one is I need negative L trim. Well, I could hook this up a little higher like this. Okay, negative L trim is right there. And then this one is taking positive throttle, and throttle is at the bottom. So I will use that. And it takes FGX. FGX is that one. And this guy here is going to take FGZ, which is right there. All right, all of these are built. Now let's put some areas around them. So these are our F forces. Okay, that one is for FGZ, or not FG anymore. That one is FZ. It's the Z component of our force vector. Okay, there is that. Perfect. Now, final touch up. We want to loop in all of these. So the way we would loop in is this last one, throttle trim, has to do with fx. So that goes all the way out. The next one is elevator trim. Elevator trim will go for fz, like that. And then the last one is moment. Moment would go, I think I got that wrong. So let's get rid of it. The moment one is gonna go to elevator trim, because once you have a trimmed elevator, you definitely don't expect any moment to happen. That's how you know that one is going to go with it. And then the alpha trim will go with fz, just like that. All right, a couple of things here is I will put a display, rotate, control R, and then let's make 3 of those. I want to capture my u trim, W trim, and theta trim. Reason being, these will act as my initial condition to initiate the model. You always want to initiate your model close to the equilibrium point. Otherwise, the model is not going to behave proper. It won't stabilize and other issues can happen. So that's like a thumb rule. You always want to initiate your model around an equilibrium point, as close to an equilibrium point as you can. This has to do with like a lot of control theories. Those who are in control theories and researching that area, you would know what I'm talking about. And so I'm putting a scope on this side, a big scope, because I want to capture the output. Actually, if I can get a scope. Okay, there is one, and then I want another one that goes for this. All right, so let's try that. Okay, so I'm gonna go to the top level, double click on the 6 stuff. I will make sure everything is starting from 0 before I do this. And another thing, I will show you in a minute. Okay, let's go into the equilibrium solver. Let's call that maybe 50 seconds would be enough. Run that. All right, looks like it compiled pretty fine. Once it compiles, what you want to do is you want to look at the values on the display, and then you want to use those values for your for setting up the initial conditions. Before that, let's actually give these gains nice value, because right now looks like the gains are pretty high, and you just have to play around with them. Always, like, these are integrated gains. I would highly recommend start out with like a smaller sprinkle, very small number, and then you can go about that. If you are not sure, you can always Google or AI to check what would be a reasonable value to begin with. Okay, there goes that. Let's try that now. And another thing, if the signs are not correct, you will be able to catch it, because ultimately we want everything to converge. If they don't converge, the signs are flip-flopped. Okay, let's see what we got, what value we have got here. All right, looks like we have a negative. All right, that looks pretty fine. Let's make sure. Okay, what I will do is I'm opening this 6 stuff block. I'm going to put some values here which would be reasonable. So back to the trim solver. Okay, and let's get that box. All right, so the first value is 49.97, and then W is negative 1.771. Okay, and then pitch is negative 0.03543. Okay, let's give that a run. All right, trying that again. Did it change? I'm gonna go back to the thing. Okay, looks like it is pretty good. Let's get to the trim. All right. 49.97. Okay, looks like this is, let's see what's going on with the scope. Aha, check that out. All of them are converging to 0. And that's what we expect to see. If all of them converge to 0, you know you have established a good longitudinal equilibrium. Another thing to check is, let's go to the top level. This v-safe velocity can stay, but other things, I am going to get rid of them. I will show you what else you can check for the top level verification and validation. So this can stay. I will remove the Euler angles. I will get gamma. Gamma was the flight path angle, but in order to do that, I have to define gamma. So let's go back to the aerodynamic block set. And inside the gravity thing, you have, so use a sum and then do a negative, because your gamma is nothing but theta minus alpha, right? So if you do a from block, capture your alpha. This is not the trim alpha, but the regular alpha. And then theta is already available here. So there is that. And this little thing is going to give you gamma, which you can do go to capture that and call that gamma, or FPA for flight path angle, whatever you like. Now let's go to the top level. Let's get our gamma here and connect that. I want to get the scope so I can configure it better. So hit on the settings, and over there you want to do your display 4 is your velocity. That is good. Display 3 though is altitude. That's also good. Display 2 is gamma now. And display 1 is PQR. That's good. Okay, now let's run this. All right, I want to see my PQR, all three of the things. They all should converge to pretty close to 0. And then this gamma is also gonna converge to 0, ideally. Altitude. And then velocity. Now with the velocity, what we are looking for. So looks like we are seeing some oscillation, but it's because the solver may be taking longer to converge them. So why don't we run this for a longer time? And check that out. Beautiful. So there is that. There is some steady state error, but we will take it. We will take it. That's not a bad one. Gamma is pretty close to 0. And then altitude is decreasing a little bit, but that's okay for now. We will deal with that when we do our lateral model. Now, one thing to make sure is, let's go back to the pilot commands. What we want to check is over here, we need to make sure everything is 0, which it's not. Maybe that's why the altitude is showing up. What you can do is you can use the slider to hit 0, or you can double click on this constant connected to the sliders and make them all 0 manually like that. And with that being said, why don't we give that another run to see if the altitude improves? Again, I'm not concerned about the altitude at this point because, like I explained in the beginning, altitude, no matter whatever altitude you are at, the equilibrium is equilibrium. The definition of equilibrium has to do more with velocity for now. And so, speaking of velocity, I want to check. Look, we gave a desired command velocity of 50, and it is able to hit that pretty close. It is able to hit the 50 mark pretty close. Is it? Looks like it is a little bit over, actually. So let's see if we can troubleshoot that real quick. All right, I got the scope for us so we can troubleshoot this at the same time. So let's see. Looks like, let's go into the trim solver. And over here for the weight, actually, we have not selected the weight. So I put the weight there, and then let's try to run this now. I want to see if it fixes our issue. So we got, okay, that looks much better now. Alrighty, so we have the velocity is pretty close to 50, and that looks promising. The altitude is decreasing, but we will take care of that altitude factor later. And gamma is now pretty close to 0. As you can see, it's like settling at about, what is 0 point? I can actually zoom into that area. Yeah, 0.07 which is pretty close to 0. So gamma is acceptable. And our PQR are heading to 0, all the way to 0. Okay, looks like that is a promising result. Hopefully that was all useful. And the last thing I would touch on is this JJ trim algorithm. And so that algorithm has to do with, like, there are so many user defined algorithms available out there, and JJ trim is one of it. Those are like entirely MATLAB scripts. You can find them on GitHub. You can find them on the MATLAB MathWorks website. And so you can use that if you know how that is operated, what are the requirements, if your model has all of the things needed. So you want to be careful with those, but it's good to know that those are the things that are out there that you can use. And so you don't have to always model things from scratch. I am doing this so that the fundamental gets cleared up, but you don't have to. Hopefully that was all useful. See you in the next video. Thank you.